Cos phi you have found. I naught into cos phi, I told you, IW. This is the second step to find IW and I mu. What is the third step? You know V1 by IZ is R naught, V1 by I mu is X naught. Hence you find R naught and X naught. This is our first objective, is met. Now second objective is to find the constant losses. The wattmeter reading itself is a constant losses. Now you see this. Now the second objective is to find constant losses. W naught is equal to losses at no load. What are the losses? I told you. Iron losses, I told you, yes. Dielectric loss, yes, I told you. I told you copper loss, yes, I told you. Stray load losses is neglected. You can add also stray load losses, but if at no load the primary and secondary current are zero, only main flux exists, leakage flux is very less. Of course, no load current is also very less, it may be neglected. Dielectric losses may be neglected. If you want exact equation is iron losses equal to wattmeter reading minus ammeter reading into R1. R1 is there in the manual which is given by the manufacturer, or if it is not there, use this method normally. Or you can say how actually manufacturer know the R1 value. Normally R1 value, see what they will do, they will have two methods. One is DC ammeter voltmeter method, or they will do Kelvin double bridge method. Now there is two method. Now since DC ammeter voltmeter method is difficult, winding may burn if transformer saturate, so they normally don't prefer DC ammeter voltmeter method, they will go for Kelvin double bridge method. See, in the name itself, when you read this, when you listen this, you might get a doubt. Kelvin double bridge method, for which it is uses for low resistance, medium resistance and high resistance, low resistance. So by if they are using Kelvin double bridge method, it itself telling that resistance of the winding is very less. And I told you in that polarity test, normally 3 to 5 DC volt is enough to flow the current in the primary, since resistance is less than 1 ohm. Now you see here, now you found the iron losses equal to wattmeter losses minus I naught square into R1. So our second objective is also met. You neglect I naught into I naught square into R1. The wattmeter reading itself is a no load losses. So first two objectives met. Shunt branch parameter you have found. You also found the constant losses. Now there is a time to separation of iron losses. Now what you will require is variable voltage, variable frequency with V by F constant. So how you will vary? You will vary using alternator. See, normally you will say alternator rotated constant speed. That is true if they are connected to a grid system. For isolated machine, you can vary the speed by changing the voltage and frequency. Once you connected it to the grid frequency is 50 Hz, then you cannot change its speed normally. That is why hunting will occur. For the isolated machine, speed can be changed by varying V by F. Now in laboratory, change V by F, speed is 120 F by P. If you vary the frequency of applied using cycloconverter or anything, frequency N will reduce. If N reduce, F reduce, means EG is directly proportional to F, EG will reduce. So speed of machine reduces. Using cycloconverter you have reduced the voltage, and using, since cycloconverter input is given to synchronous machine, the voltage itself is reduced, so V and F both is reduced. So we need one more equipment called frequency meter. Since you are varying the frequency, you need frequency meter to measure the frequency. Now hope you have understand how we are maintaining V by F, varying V by F, but V by F constant. And I have told you, since V by F constant, B max is Wi equal to AF plus BF square. This I have told you in last video. When V by F is constant, hysteresis losses is proportional to F and eddy current losses is proportional to F square. Now I bring the F to downwards, then it become Wi by F equal to A plus BF. This is a equation of straight line. Now since A is constant, I kept here, with slope theta B is moving. With slope theta B is moving. What is now see here, I drawn x-axis as x-axis as f, y-axis as w by f, and b is varying like a straight line. Now find the tan theta. Tan theta represent the slope. The slope is what? Coefficient b. So now examiner may ask what is the coefficient in w by f versus f graph, that is the constant b of eddy current losses. It represents constant coefficient of eddy current. Now hope how I drawn this. This is a straight line equation with y-intercept as a and slope as b. Now you move ahead. Now let us solve a question. Now suppose a 400 by 200 50H transformer is given. Open circuit test, as I have told you, conducted on LV on 200 volts 50 hertz. The iron losses you got, suppose 100 watt. He conducted a test on LV, he got 100 watt. Now he conducted the same test on HV, that is 400 volts at 50 hertz. What is the iron loss? The question is, what is the iron loss? See, iron losses is depend upon Bmax. If you apply rated voltage and rated frequency, the iron losses will be constant. The answer is 100 watts only, because on secondary 400, see on first on secondary you applied, that is LV side, 200 volts you applied, that is rated voltage, frequency 50 is rated, so you got rated iron loss. Now you conducted this test on 400 on HV side, that is rated voltage only you applied, rated frequency only you applied, so iron losses remains constant since V by F constant here, this is rated value is applied. So it does not mean that if you conduct the iron losses at HV side, we will get wrong answer. No, there might be a reason that accuracy might be reduced. That is, no load current is less, reading must be difficult. Now let us see, and the source you need to provide high side. One more thing, let us see another objective. Open circuit test at rated voltage and lesser frequency, then what is the iron loss? Suppose it is conducted at LV with rated voltage but frequency is reduced. Now when you reduce frequency, Bmax is increases, Bmax proportional to V by F. When Bmax increases, I mu increases, because I mu produce the phi. So I mu increases, Bmax increases, there may be a saturation. When saturation will come, what will come? I have told you, harmonics will come, which will be discussed later. Now Bmax is not constant, hysteresis losses, V by F is not constant. See, V is kept constant, F is decreased, V by F not constant. You will find that the hysteresis losses V power 1.6 by F by 0.6. Since F decreases, hysteresis losses increases. Eddy current losses is proportional to V square by F into F square. Since V is constant, eddy current loss is proportional to V square. Eddy current losses will be constant, but hysteresis loss will increase. When losses will increase, IW will increase. Here I mu increases, IW increases. So I told you, never decreases the frequency lesser than rated frequency. Now take another question. A 400 by 200 volt transformer, if open circuit test is conducted on LV, this is important. In LV side, the reading of ammeter and voltmeter are 5 amperes 100 watts at 50 hertz. What is the reading of wattmeter if test is conducted at 150 volt? See here, he keep the frequency as constant, but voltage is increased from see here 200 volt to, sorry, voltage is decreased from 200 volt to 150 volts. Normally you see, voltage normally cannot be increased since insulation burn. If hypothetical case in examination came, you have to accept it. Now the question is telling that in first case a 200 volt 50 hertz test is conducted. During second stage a 150 voltage is reduced to 150 volt 50 hertz. Frequency is constant. What is total wattmeter reading he is asking? See, first see the options. I haven't mentioned the option, but as per option you have to proceed. Now see, here he does not mention anything. He mentioned as 100 watt. He does not separated the hysteresis and eddy current losses. To reduce the hysteresis and eddy current losses separately, if you want separately, you need V by F. Varying V by F, you will separate the eddy current and hysteresis losses. To draw at least the curve which I have shown you, you need at least 2 points to draw a straight line. But here he is not given any such data. See, listen here, he does not given any data, he is only given 100 watt as total losses. In that case, when V by F is not constant, hysteresis losses is proportional to, see here, V power 1 by 6 and F power 0.6, and it is hysteresis loss, eddy current losses is proportional to V square. Since F is constant, you remove the F term. Now one is proportional to 1.6, another is proportional to V square. Now you approximate Wi as V square. To listen here carefully, this point is important. You can approximate iron losses proportional to V square only when V is varying and F is kept constant, because F is in denominator in hysteresis losses and you assume the F is constant. Since given in the question only voltage is varying, frequency is constant, now in this case only you can assume that Wi is proportional to V square. If you solve, then you get iron loss, total losses. Hope you have understand the significance here. I have added this question. Now move ahead. Since we met 3 objective, now we will move to short circuit test. What are the objective of short circuit test, friends? To find variable losses. In first case, you find the constant losses. Now to find series branch parameter, to find percentage R, percentage X, percentage this. In the open circuit test, we need to separate the losses into 2, hysteresis and eddy current. Here we are finding the percentage R, percentage X and percentage Z. This is very important and conceptual question, conceptual topic. Listen carefully. Now, since here rated current is needed to find I square R, but not wasting the output power. This test, that is, we need to find the variable losses in the transformer. So you need the rated current here, because copper loss, you need to find what is the maximum value of copper loss at rated load. You need current, but your aim also not to waste the output. See, in open circuit test, secondary is open, so output is 0, losses are very less, I naught current is flowing, only constant losses you are measuring. Here if you allow full load current, I square losses will be more. So to reduce the losses to 0, we are short circuiting the secondary. Means I square R is 0. Since R is 0, we have short circuited. The losses at the output is 0. Output power is not wasted here also, like in open circuit test. Now by short circuit test, another winding, slowly increase winding such that I equal to I rated. We need this test at rated current, slowly by short circuiting the secondary, slowly increase the voltage source. Since I have taken a variable voltage source such that I equal to I rated. Now you know that power on primary and secondary approximately same. VLV ILV equal to VHV IHV. VLV is less than, since low voltage winding is less than HV, current at LV is more than current as HV. This you know, that at low voltage current is more, at high voltage current is less. So since we needed rated current here, we always prefer the side where current is less. So we do this test on HV side. In polarity test with DC source we are conducting in HV. In open circuit test we are conducting at LV. In again short circuit test we are conducting at HV to maintain the low current, since we need rated current here. Now there is two concept note here. One term is steady state short circuit current. Steady state short circuit current means, suppose if we apply rated voltage, suppose 400 by 200 volt transformer is there, we are doing at HV. If we apply to 400 volt, the current which will flow is called steady state short circuit current. This is more higher, because see, we have short circuited, load resistance is not there, winding resistance is very less. Since I have told you, you are using this, see here you are using Kelvin double bridge method. It itself saying that resistance is very less. Since the resistance is very less, if you apply rated voltage here, transformer will burn. So that current which flow when we apply rated, you observe a rated voltage source, that is called steady short circuit current, which is very large. Now you see rated short circuit current. Now you see the term rated short circuit current. The current here we apply a voltage such that using variable source the current is 5 full load, which mentioned on the nameplate details of HV side. Suppose HV side is 10 amperes current rated, we vary the voltage source such that 10 amperes is flowing on HV side. So the voltage source is required now is very less since short circuited. Now I equal to I full load. Only we required 5 to 8% of full load voltage. Suppose 400 by 200 volt, take an example. Now we required, suppose only 10% means 40 volts, 5% means 20 volts. If we apply 20 volt AC, it's enough to flow the rated current under short circuit condition. Hope you understanding the difference. So during short circuit test, very less voltage is required to flow the rated current. Now Bmax is proportional to V by F. What is its consequences? Bmax is very less because B is less, V by F is very less, and it is not constant. Bmax is also only 5 to 8%. It's proportional to voltage. Voltage required is 5 to 8%. So Bmax also 5 to 8%. So the Bmax is very less. So the core losses under short circuit condition is very less. See, under open circuit test, only no load current is flowing, so copper loss is neglected. In short circuit test, only 5 to 8% voltage is applied, voltage is less, so we are neglecting the constant losses here. Hope you have understand. First objective is to find the full load copper loss. The wattmeter reading showing itself is full load copper loss. Hope first objective is met because iron losses is less. See, short circuit losses, copper loss neglected in open circuit test, copper loss neglected. In short circuit test, iron loss is neglected. Now move. See, second objective to find R naught and X naught, series branch parameter. Now wattmeter reading is mostly showing the, I told you, mostly showing the iron losses. Iron loss equal to I square into full load. How you find I? I is found by ammeter reading. So ammeter reading, wattmeter reading by ammeter reading giving R, and Z equal to V by I, voltmeter reading by ammeter reading. Now you find Z, you find R, you find X naught by root of Z square minus R naught square. Hope you find how you know how to find this. Understand R naught and X, Z naught and X naught. We met our second objective also. Now I have discussed this also. See, shunt branch parameter R naught is greater than X naught. See, I told you I naught is around 5 to 8% of full load. In that, I mu is around 5 to 5% and IW is only 2%. So IW is less, means it resistance is more. Indirectly, it resistance is more. By that concept, shunt branch RW, I wrote here wrong, sorry for that. RW is greater than XW, and in series branch R naught is less than X naught because we are keeping R and X in series, and so that we want lesser voltage drop, so that regulation is good. We make of, I told you, all power transfer is made up of copper winding and distribution made up of aluminum winding, so that resistance is less. So R01 is less than X01, whereas RW is greater than XW, or R0, no load component, is greater than X0. So a comparison is made. This was asked in engineering service, which is the lowest series resistance is lowest, whereas highest is shunt branch RC or R0, which representing the core loss, and R01 is the lowest, which is representing the I square R losses, copper losses. This is the correct sequence. Now hope you have understand. Now we have found that first two objectives met. Now let us see procedure to find percentage parameter. See, I told you, already discussed this. Percentage as equal to percentage copper loss in the last class. Now what is the percentage? Percentage means to compare with somewhere. See, total copper losses is given by wattmeter reading. This is wattmeter reading by VA rated of the transformer. It is already mentioned on the nameplate details. So you find percentage R. Now what you need, percentage Z. I told you previously Z. See here, VSC is equal to ISC by ZSC. So VSC by ESC, you again percentage, you need Z, means you have to compare. So both side dividing by E1. Now VSC by E1 equal to ISC Z01 by E01. I already told you, you cannot compare the R and Z, so you will convert into voltage term. So this is representing percentage Z. So VSC is measured by voltmeter, E1 is mentioned on the nameplate details, so that by voltmeter reading you will find percentage Z value. Percentage Z is found by voltmeter reading. Percentage copper loss is made by is measured by wattmeter reading. This is measured by wattmeter reading, this is measured by voltmeter reading. So percentage X is equal to root of Z square minus R square. Percentage Z is Z square minus R square. Sorry for that. Now since you won't need wattmeter here, this question was asked in finding the percentage value in short circuit test, which of the meter is not required? First wattmeter, second voltmeter, third ammeter, D none of this. Answer is ammeter, because percentage R is measured by wattmeter, percentage Z is measured by voltmeter, so that you won't require here ammeter. Hope you understand what I want to say. Now take that. So take here a question: a 5% rated voltage is required to rated short circuit current, then percentage Z. See what it is telling, that a 5% current is 5% voltage is enough to flow the rated current. That is 100% current to flow, 5% of rated current voltage is enough. Then this 5% is called percentage Z. See here, percentage Z equal to VSC by E1 into 100. I already told you cannot compare Z, so you will convert into terms of voltage. See what percentage VSC short circuit voltage by E1 will always give in terms of impedance. See here also you got percentage Z by VSC by E1. Similar case here. Now he is given 5%, he is comparing with E1. Now if 5% is enough, that is equal to percentage Z. So whether he is given percentage Z or percentage of voltage required to flow the current, all will have same meaning. Examiner may frame the questions in any way, you must able to answer. Now a 2000 by 200 volt transformer has percentage Z equal to 8%, then voltage applied on HV to flow the rated half rated current on LV side short circuited. It means if LV side is short circuited, what is the voltage required to get half of the rated current? See, percentage Z means percentage of value required, voltage required to get full load current. Since this test is conducting on HV, is mentioned that LV is shorted, means HV is conducting the test. 8% of 2000 is 160 volt. Now he is required half of the rated current, means 80 volts. This was asked in GATE. Hope with my video lecture is helping you to solve both engineering and GATE questions in simple manner. If you have any doubt or you want me to start any subject, just comment in the comment box. I am ready to start any subject because GATE exam is very near. And if you like my video, give a thumbs up. Similar case, voltage is constant and frequency is reduced. Now take R is constant. Now X01, if frequency is reduced, X01 is reduced, Z01 reduced. Power factor is R by Z. Power factor increase. Copper loss increases because I increases. What that is, copper loss is increased. So here if you reduce the frequency, copper loss will increase. Now this all about here. I will stop this video here. Thank you for listening. Please hit the like button if you like, and if you want any subject me to start, comment in the comment box. Thank you.